Hello all. And so today we're going to be talking about the vehicle routing problem and some constraint programming approaches to be able to solve this problem. So I just thought I'd start off with a bit about NICTA. We're a relatively new organisation, and we really want people to know who we are and what we do. So this is who we are and what we do. We've only been around since 2004, but we have labs in 3 of the major cities of Australia. We're up to 700 researchers if you count our PhD students as well. So it's about 300 PhDs, 400 researchers in the organisation now. We're currently government funded, although it's actually now moving, and we're getting more and more input from industry, because our focus is really applying the best research that there is around to industrial problems. So we do fundamental research, but also applied research, and the stuff that I'm going to talk about here is stuff that's been applied in industry. And our main areas of research are those 4 that you see here, and this one is under the banner of infrastructure, transport and logistics, of course. Okay, so what we're going to be talking about today. Look first of all at the VRP and why it's an interesting problem to be studying, both in terms of its use and its interesting aspects. We're going to have a look at some traditional, and by that I mean non-constraint programming approaches to solving the problem, and then move into looking at a CP model. That model's got, we actually look at a couple of different ways of solving that model, and in probably the least exciting part of the talk, I'm actually going to do some hand propagation of a set of constraints. But I hope that you'll understand the use of constraint programming by going through this rather tedious exercise. And then we'll have a look at one of my favourite methods for combining constraint programming or solving solving VRPs with programming, and that uses the large neighbourhood search. Okay, so what is the vehicle routing problem? It's one of those nice problems that you can state nice and succinctly. You give me a set of customers and a fleet of vehicles that you want to use to deliver something to those customers, whether it be goods or a service, and I will give you back a really good set of routes that visits all of those customers exactly once and doesn't exceed the capacity of those trucks, and hopefully it will be at minimum cost. And so what does that look like in practice? So here's a set of customers, and here is a solution to that problem. So this is one of the classic benchmark problems in VRP. It's got this lovely separated, clustered structure. This is what it looks like in the real world. This is actually I think there are 64 routes in there that deliver to all of the customers that take bread in Sydney. And that's what it looks like in the real world. So the VRP is hard. Now this little symbol here, my stuff. While I'm looking for my caramello koalas, I want you to be thinking about the one proof or the one sentence proof that the VRP is hard. Reduce VRP to a well-known hard problem. And the rest of the proof is? Excellent. That earns you an Australian delicacy, the caramello koala. So indeed, it's the VRP. If I had a VRP solver, I could solve the TSP with one. If I just gave it one vehicle with an infinite capacity, I could solve the TSP. So it's NP hard. It's in fact NP. Yeah. So another reason for solving the VRP, it's a really important problem economically. So I know Australia best. And so I'll give you the figures for Australia. I think they're similar, but not exact for the other countries. Sorry. So 9% of Australia's GDP is tied up in actually moving things around. and the logistics part accounts for 10% of the price that you actually pay for stuff. Now, Australia might be a little bit different, because it's a relatively big country, and the next caramello koala goes to somebody. So people don't realise just how big Australia is. So I thought I'd throw this one in. Compared to the USA, continental USA, how big is Australia, do you reckon? Percentage figure, nearest 5%. Any guesses? 110. A third? A third is wrong. 100 is not right within 5%. 90 is close. Okay. Who said 95? That's you? Yeah, I think you better come down or I'll knock somebody out with that. 95 is correct. You can come and get that at your leisure. Yes, so Australia is actually almost the same size as continental US, and for our Europeans, it's actually even bigger than the continental Europe. Isn't that interesting? Okay, so that's enough about Australia. We'll concentrate on the VRP now. So, VRP, what we're given is, for each customer, we want to know how much stuff they've got to be delivered, and in the case of a service delivery, that might be not at all, but they're just interested in the time. But let's stick for the moment with the amount of stuff that they need and the cost to travel to every other customer. So I'm going to be developing these routes around all the customers, so I need to know what are my options. If I'm here, where can I go? For each of the vehicles in the fleet, I need to know basically how many I've got and the capacity of each of the vehicles. And so we need to divide up our customers into the group of customers that each vehicle will visit, and then within that group, what is the order of visiting? And I want to minimize my cost. And cost here can mean various things. So the objective function for your classic academic studies is first of all to minimize the number of vehicles, and then to minimize the total cost within that number of vehicles. I work in the real world, and so I'm more interested in what happens in practice. And pretty much every single time a company has come to me to solve this problem, they said, here is our fleet of vehicles. You actually don't have a great deal of flexibility in how much I can move that around. So actually, the thing that they want to minimize is a combination of time and distance. So they know from their records that how much they have to change their tyres, how much the petrol use is, what their leasing fees are on all of their vehicles. So these are elements that they can put to the amount of time on the road and the amount of kilometres on the road. And the vehicle numbers are fixed. So this is what's interesting when you move out of academia into the real world, is that each time you go to a new customer, the particular rules that apply at that customer are slightly different. Even the particular types of constraints can even change the way that you want to solve it, and we'll look at that a bit later. The constraints that apply are looked at various constraints. In fact, hundreds of different constraints have been looked at in the literature, but mostly in combination, in isolation. Sorry. So the people will look at a time window constraint, or they'll look at a capacity constraint, or a pick-up and delivery type constraint. But what we're interested in is being able to solve all of those simultaneously. So let's just have a look at a few of those individually. So time window constraints is pretty much every problem that you actually get in practice has one of these. It says a customer is allowed to specify when they'll actually receive the goods. So they might say between 9 and 11, or between 9 and 11 and 2 and 3 is acceptable. So as soon as I get time constraints, I then need to know, as well as the distance between every pair of customers, the time between every pair of customers, and how long I'm going to spend at each of my customers. Now, in particular variants, you can also have travel times that are dependent on the time of day. So at peak time, it might take me longer than in the afternoon. And I can even have vehicle-dependent times. So a B double, which is the big trucks that can take 2 containers, is going to travel a bit slower than a little van. We won't talk about those type problems here, but they can be using the stuff that we're going to talk about. And this stuff makes the route harder to visualize. So here's another classic benchmark problem from the literature. This is it solved without time windows. This is it solved with time windows from that are in the benchmark problems. So this kind of stuff is why it's really hard, A, for humans to solve these types of problems, because if I was to sit down with this set of customers, it would take me a long time to work out that this is the best set of routes to come up with. Also, it actually makes it hard for the solving routines as well, because there's a lot of unobvious stuff that has to be done to come up with this solution. Okay, another very common constraint in practice is the pick-up and delivery type constraint. Here, we're not just, in the classic VRP, we've got, usually you think about it as a bunch of stuff at the depot that we're taking out to our customers. It actually works in the reverse as well. A bunch of stuff at the customers that we're bringing back to the depot is exactly the same model. But in the PDP, the stuff is in the customers. So we're sending out a truck and picking up something at one place and taking it to another. We might stop along the way to pick up something else, so that we end up with a load profile that looks like this, where we pick up some stuff, we drop off some stuff, we pick up some stuff. So our capacity constraint now, in the original one, we only had to really worry about the capacity constraint at the end. Now we have to look along the whole of the route and make sure that the capacity stays visible to the whole of the route. And just one more variant that's studied in the literature quite a bit, and which is also very interesting, is profitable tour problems. Here, we don't have to visit all of the customers. Usually, that's the first thing, is you have to visit all the customers. But in this one, we're asking the question, is it actually worthwhile visiting the customer? Or do I actually have time enough to visit the customer? And so, as well as deciding which vehicles visit which customers, you're also deciding which customers to visit. And you want to choose the subset that gives this equation here, the profit from visitors. So you assume that I know how much I can make from visiting this guy here and visiting this guy here, and I'm going to collect the profit as I move along this and subtract from that the actual cost of that tour. So what I'm guessing is that even though this guy here is only a slight deviation away, that cost of that deviation doesn't justify picking that guy up. So he's obviously got a very small profit. Okay, and then you get even more rich problems. So this is now a real strong theme in the VRP literature, is looking at these so-called rich VRPs, which try and include as many of these constraints as possible. So Asvin Goel defined this particular one, the rich vehicle routing problem, that includes not just not just a single time window, but multiple time windows between 9 and 11 or 2 and 3. Multiple commodities. So I might have a constraint that applies on the total weight and the total volume and the number of pallets that I can fit in my vehicle. I might have different sorts of vehicles. I might have vehicles that are a few small vans that I can use to send around, a few middle-sized vehicles, a few larger vehicles. They will each have their own cost profiles, and choosing the right mix is part of the problem. And compatibility constraints. This is where I might have a couple of requests where I might say, this request can't be on the same vehicle as this one here. I can't move petrol and food on the same vehicle. Or I might have to say, these must go on the same vehicle. PDP is an example of that. The pickup has to be on the same vehicle as the set down. And I might have customer vehicle incompatibilities or compatibilities. This vehicle has to go to this customer. We did a job once with a customer, conspicuous driver constraint, we called it. He was actually conducting an affair with one of the secretaries, and so this vehicle had to go to that customer for a few weeks, and then after a couple of weeks, it was this vehicle had to go to a different customer and no longer was allowed to go to the first customer, which is the other one. This vehicle can't go to that customer compatibility. It's more often this vehicle can't physically to actually drop off the stuff that makes this one a real constraint. Other constraints that pop up, fatigue rules and driver brakes. These are really important and really hard constraints. So in the European rules for a valid driver tour. So these things say, if I've been driving for more than 12 hours, I need a 2-hour break. If I've been within any 48-hour period, I need one break of at least 8 hours, followed by not more than 2 hours work. In any 7-day period, etc., etc. Once again, Asvin has shown that even checking whether a given tour can be implemented within the driver constraints is actually an NP-hard problem. So these ones are really, but I mean, it's useless putting out a tour that doesn't meet these constraints. You'll get in trouble. So these are ones that you have to worry about a lot. Vehicle reuse, where you have a vehicle and you send it out on one tour, it comes back and refills and goes out again. The classic VRP can't handle that. You can actually do things that are called quick hitch, where you sit a trailer in your depot and you get somebody else to fill up that trailer with the stuff that needs to go out, so that when your prime mover comes back, it can go out and do one tour, come back and really quickly drop its old trailer, pick up a new trailer and go straight out, which might save it an hour or two in its loading time. But this changes, again, how the timing of that route. All of the time windows in that second half need to know that I've got a quick hitch or not in order to be feasible. Variable loading and unloading times is another one. Limited docks, where I might have 5 trucks, but only 3 docks can fill up at one time. What order do I fill up the trucks in order to get them out into their to do their work? Okay, so these are just a few of the wrinkles that you see in solving VRPs. Actually, most of those appear in the literature now. The literature is getting nice and rich in these wrinkles, but certainly the kind of things that you see in the real world. So I'll just do a quick survey of the types of methods that are usually used to solve these. And I'll concentrate on sort of the smaller size problems. There are particular methods that scale up better than the ones that I'll present here, but these are the kind of typical stuff that you'll see at the moment. We've already done that. So it's NP hard in the strong sense, VRP. So you really, if you're looking for exact solutions, it's usually only in the sort of 20 to 50 customers that you'll find an exact solution. So basically, we're looking at heuristics to solve the problem. Just out of interest, this is the ILP that will solve it exactly. I don't have time to go through this in detail, but I'll just point out, you've got here constraints that say if I go into a customer, I need to come out of it. If I go into it, I go into it exactly once, I go out of it exactly once. If I go into it, I go out of it, and I go out of it on the same vehicle. Sorry, XIJK here is I go from customer I to customer J using vehicle K. And here's the capacity constraint. All of the customers that I go out of in a solution on vehicle K is less than the capacity of that vehicle. And this is the nasty constraint. This is the one that makes ILP not work. The subtour elimination constraint. So if you ignore this constraint here, all of these can be satisfied by a setup like this, where I've got the depot down here and I've got one tour here, and then mysteriously you've got this one here that has, even though I've said there's only one vehicle, I actually need 2 vehicles to do that. So you need to have something that stops you creating subtours, and that's really where the ILP breaks down. Another ILP formulation is the so-called column generation constraint. This one is kind of interesting. I've got here, each of my rows represents a customer, and my columns represent a potential route. So this first column is a potential route that visits customer 1, customer 4, and customer 5. Now, I don't tell you what order that they're stored in, that they're visited in. I store that separately, but for that route, there's a cost of 89. Second route visits 1, 2, and that's all, and has a value 76. So for that one, all I want to do is to, my decision variable now is which of those columns do I want to use. I know the cost of each of those columns, and my only restriction is that I have to cover all of the customers. And unfortunately, I need to make it integer. I can't visit a customer half with one vehicle and half with another. So I can solve that. I really don't have time to go into this, but I can solve that using the reduced costs, and what comes out of it is a constrained shortest path. The nice thing is that this is actually a really nice application for constraint programming as well, because the constrained path that I need to create is basically has to observe all of the constraints that you're putting on your routes. And so it's a constrained path problem, and so CP is actually really good at doing that. Okay, so if we move out of the exact methods into the heuristic methods, most of them operate as a construct and improve. So I'll have a quick, so this is an example of construct and improve. Using insertion. So here I have my all the customers that I want to visit, and I've inserted my first visit in there. And now I need to decide which visit to insert and where to insert it. I've decided to insert this one, and in all of these, I'm just going to insert it in the position that increases the cost by the least, which is a fairly usual method of choosing where to insert. So the method I'm using is actually which one increases the cost by the least is my which visit criteria, and also inserting it where it increases the least. So you can see here, even though I'm building up nicely, the place that increases the cost by the least actually introduces a loop here, which is not very nice. And you can see that we're getting some horrible little guys left behind here, so that after a while, I'll actually skip to the end here, and that's the result of creating a solution from nowhere. You can actually improve that kind of thing by introducing these some seed nodes, where in this case I've just chosen the most distant customer from the depot, then chosen the most distant customer from that customer, then the most distant customer from those pair of customers, etc., until I ended up with these seed customers. And seed customers really help to guide the creation of a route. So when I create this one using exactly the same rules as to which one to insert and where to insert it, both of them increasing the cost by the least, I end up with that route. And that's actually the best known solution to that problem. Okay, and just out of interest, the decision as to which visit to insert is a really important decision. So in this next one, I'm going to keep where to insert it the constant. It's always going to be the position that increases the cost by the least. But here's one just using a random selection of which visit to insert, and I get that. A different random selection of which one to insert gives me that. A different one gives me that. If I use C, sorry, that was actually using seeds. They were the good ones. I'd forgotten that. These ones are use no seeds, and you can see that using no seeds, you get even worse routes by not by just using a random thing. So this to me was interesting. That you can the choice as to which visit to insert gives you a hugely different performance of your algorithms. Okay, another way of constructing is using the savings algorithm. This is a classic one. don't you hate it when somebody comes along, 1964, the field is just only just getting started, and somebody comes up with a method that is still used today. And it's not a terribly obvious one, but they really nailed it. So what you do is you work out the saving. So given that I'm going to go to I and J, what's the saving if I go directly from I to J? And now I can order all of my SIJs, so it's got the biggest saving at the top of the order, and I say, okay, let's put those two together to form a new node and recalculate. I can actually build up a node that actually represents a whole bunch of nodes and still calculate this SIJ and just iteratively join them together. Another common technique is 2-opt and its associated ones. For 2-opt, I remove 2 arcs and replace it by 2 arcs. So in this one, I'm just going to remove these 2 arcs and replace it. There's only one way of replacing them, which gives me these 2. That leaves this little section here going the wrong way, so I reverse those. And that's a 2-opt move. And I can look through my entire solution and find whether there's any of these 2-opt moves that improve the solution and just repeat. 3-opt moves 3 arcs and replaces it with 3 arcs. Large neighborhood search is one that we'll look at later. It's a destroy and recreate one where I just basically destroy part of the solution and then recreate it using my favorite construction heuristic. LNS is really nice. If you have a construction heuristic that you think is fairly reasonable, LNS is a really good way, that basically a local search for free using LNS. We'll come back to that, so I'll skip it for now. One of the very successful methods for VRP is variable neighborhood search. So in this one, I have a bunch of different neighborhoods, and each neighborhood is slightly larger than the previous one. So I start off with my smallest neighborhood, here a 1 move. All I'm doing is moving 1 visit to another route, and I'll search for all possible instantiations of that. Where can I put this, just move this 1 customer, and I'll look at every customer. If I find an improving move, I do it. If I can't, I move out to my next largest neighborhood. Maybe a 1-1 swap, which is swapping pairs of neighbors. If I can't find any 1-1 swaps that improve the solution, I move down to the next one, 2-2 swap, etc. As soon as I find an improving mood, I go back to my top one and work my way through the list. And by changing which set of neighborhoods I look at, I can end up with some really good solutions. And that's what I just said. Genetic programming has also been applied to this quite successfully. Here I generate a population of solutions, and then I use some good old Darwinian cutthroat. Breed them. I take parts of one solution and join them with parts of the other solution. I do that until I've doubled the size of my population, and then I chop it in half. I kill all of the poorest performing solutions and keep the top half. There are several in the benchmark set that Syntef keeps. Genetic programming has quite a few of the best known solutions. Okay, and there's a whole bunch of other methods that have been used over the years. W-search, simulating, ants, bees, the works. Okay, so that's the kind of stuff that's been used so far. What's wrong with that? Nothing if the exact problem that you've been presented is the one that you need to solve. The trouble is that as soon as you get a new constraint, you end up in all of these ones having to come up with new code. And it's often code that's right at the heart of your is this legal test is one of the most basic tests, and it's often the most complicated because you've got all of these considerations about time and distance and weight and compatibility kicking around. So you end up with code that's hard to maintain and often hard to run. So CP is, well, we're at the CP conference, so you knew that I was going to say that, right? CP is a potential answer if you need a system that can respond to new constraints easily. So the nice thing about CP, I've given a nice expressive language for representing my constraints. Each constraint is encapsulated. This is really nice. I can go away and write a constraint. If I get a new constraint that says, I did it yesterday for a test problem in the bike movement for in Vienna. Only one vehicle can visit every location. I can code that up, and it sits as a nice little ball, and basically needs to only know about itself. It doesn't need to interact with anything else. And yes, they interact naturally. The disadvantage is, I'll tell you in a moment, a difficulty in representation, and because of the T, it can be a bit slower. And so a bespoke program will almost always be either faster or better for a particular program. But if you want a system that you can quite easily tailor to the new situation, the new constraint that comes along, then constraint programming is definitely worth the thought. Okay, so two ways to use your constraint programming system once you've developed it. One is as a rule checker, and the other one is to use it properly. By that I mean that what I can do is, for instance, I can use my classic, any of those improvement methods that I've just talked about before to create a new solution, and then I can use my CP system and simply say, is this a valid solution or not? That's a perfectly reasonable way of doing it, but because there is no interaction between those two sides, there's nothing in the CP system that can say, actually, it was your constraint, your capacity constraint that just broke. That feedback, I'm going to test lots of different solutions that keep breaking that capacity constraint without any feedback. And so it's really not a very efficient way of using a CP system. Okay, so let's have a look at a CP system. Now, this was where I was going to have a little break for people. If you're getting a bit blah, you want to just stand up and shake out and come and collect your koala, caramello koala, Louis Martin. I have a few to spare. Does anybody else want a caramello koala? You even know what they taste like. Yeah, sure. Yeah. Sorry? Yeah, I actually specifically, they're really good for the larger size problems. I'm talking about the sort of 400 to 1,000 type problem that... Yes. And in fact, that's exactly what we do. Create clusters with pseudo time windows and pseudo capacity demands and things like that. No, I won't. Not today. Yeah. We actually have a relationship with a data provider who has all of the roads and all of the speed limits, and we work all that out ourselves. Yeah. We actually store the whole cost matrix. Actually, you can. We do.
You also hear the feedback loop, right? There's a feedback loop somewhere between the mic and the...
Okay. More or less the same. In terms of TSP with site constraints, I would say it's more or less the same. TSP on its own, then you know, Concord is an ILP solver, a TSP solver based on ILP that is actually very successful. But they've spent a lot of time on specific cuts for the TSP.
And it doesn't work for the same.
No, as soon as you get a side constraint, you're sunk.
What is the side constraint? Red line.
Yes, exactly right. Why?
Because it seems like that often this side sounds relatively.
Yeah, historical reasons, I guess.
We use a conventional CP solver.
Yes. No, we just use classic. Yeah. 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 Okay, let's press on. So I was aware that 90 minutes is a long time to just to sit there and concentrate. So let's see how we go. Okay, a CP model for VRP. So first of all, we need some data, and the data that we've got, I've kind of already talked about a bit. So we need locations. So in the model that I'm going to present, and it's not a universal model, but the model I'll present has fixed locations, so that's where things happen. So this is either where your customers are or where your depots are. Metrics is an important concept. This is things that change from I to J. So it's things like distance and time and cost. You need to know between every pair. And so for now, we'll just worry about the time between every pair IJ and the objective cost I to J. Now, I'm going to assume that they both obey the triangle inequality. It's actually not always true. For instance, the shortest time path is not always the shortest cost path. And so if I'm going to be developing my routes to minimize cost, sometimes that's going to break my time triangle inequality. And in a CP context, that actually matters, but I'm just going to skip over that and pretend it doesn't exist for now. Commodities, I'm going to have multiple commodities. Weight, volume, pallets, whatever you need. And I'm going to use the name commodities for the stuff that I'm moving. Okay, then we move to our customers, and we're going to have a fixed number of customers. We're going to call that N. And for each of our customers, we know the demand for each of the commodities. And we're going to introduce this concept of a value for a customer right from the very start. So this is how much do I suffer if I don't visit this customer? And I'm going to give that, call that VI. And if I'm in a time window type problem, as I usually am, then I know the earliest time and the latest time for arrival.
So, to which extent would your method break if you don't have the R
Yes, it's true.
You have, in the city distribution, especially in Europe where things are outlined, you physically cannot enter or exit because the city center for a lot of the time. Mostly it's like either or three, there all right.
Yeah.
You just can't go.
Look, we're actually right now writing up all of the soft constraints that we have. The system that we've developed has soft constraints for time, capacity, route compactness and robustness and a whole bunch of other stuff. But I'm not going to talk about that today. Basically, what I'm talking about is the hard time windows. So that's the absolute extent. You can add stuff into your objective. That gives you, we use a piecewise linear function that says within that time window there are various penalties for arriving at stages within that. And then there's a method due to Heuristic which lets you calculate when to arrive to minimize a sequence of time windows. But
It's short visit that will hold up some gymnastics that you need to do, but all that you're going to talk about here will hold up by
yeah, just for this one, I'm just talking about the pretty hard, straight-up CP stuff, which, yeah. And yes, and we also know the service time, so how long we spend at each of the customers. Our vehicles, we're going to assume for this that there are n vehicles, and each vehicle does exactly one route. Once again, we can get around the fixed routes, but we'll just assume that for now to make it easy for me to talk about it. And we know the capacity for each of our commodities on each vehicle. And our vehicle is going to start at a particular location and end at a particular location, which may or may not be the same. And we know the time that they're dispatched and the time that they have to be back. Okay, so we have a solution, which is a set of routes, one for each vehicle. A route is made up of a sequence of visits, and some visits serve a customer. So this is a little trick that is pretty common. You have the special visits, which is the start and end visits for a route. That lets you talk much more generally about all of the visits on a route being, or sorry, all of the stops on a route being a visit. I don't have to worry about the first visit being somehow different. I can just go straight to my start visit and I know exactly where that is. And the nice thing about the start visit is that just like normal visits, it has a location, it has a time window, and it even has load. It's got a load 0 usually. But its duration, for instance, can be set to the load time for the truck to make that all work. So in the CP, we need to reference all of these things. So our customers, we're going to reference in the set 1 to N. Routes, we're going to reference in the set 1 to M. And we're going to have this special route 0, which is the unassigned list. And so this is where customers that aren't being visited get visited by the unassigned route. And visits, so normal customer visits are indexed by their usual, by their index in 1 to N. Start visits are the next block. End visits are the next block. So we've got nice domains for all our variables. Okay. The nice thing about this is that any solution is now, what am I trying to say? I don't have to fail because I couldn't route all my customers. If I've got a few customers that I couldn't find a space for, they sit on the unassigned list and they are part of the solution. I don't have to say, oh, this last visit, 3 seconds outside its time window. Sorry, I'm not going to tell you anything at all about the solution that I've just returned. I can actually return an almost complete schedule, a schedule with 999 of the 1,000 customers in there and this last customer. And I can even say about this last customer, the reason why I didn't insert that was he was 3 seconds late for the time window. And that gives me an indication then of what I need to do. Some CP systems will, if you don't have the unassigned route, then you have to assign all of the customers or you get no information back at all. So this is a kind of important practical consideration in designing these things. So an example of our vocabulary here. So here are our customers. I've got 5 real customers, and our start visits are the blue ones, the end visits are the purple ones. Here's route 1 and route 2. Okay, and I've gone through those. Yeah, you need just these special ones. VS is visits that have a sensible successor, and the visits that have a sensible predecessor. With our start visits and our end visits also get a name. Okay, so we have uppercases stuff that we know that is basically the starting data for our and our decision variables. Okay, so the usual, well, the way that I model it is using both successor, predecessor, and root variables. So the successor SI gives the direct successor of I. So this tells me if I'm at I go to SI next. And so I've got the domain of all my SI variables is VE, so that's all of the normal visits plus the end visits. I need SIs for all of the visits in VS, so that's all of the normal visits plus start visits. That is to say, I don't have SI visits for E. Oh, yes, I do, but they're at 0. Okay. Predecessor variables are just the inverse. What is the predecessor of I in the root? Now, this is actually redundant. I don't need that, but there's some empirical evidence that having both predecessor and successor variables help in and so we'll maintain the PIs as well, which is the predecessors. And then the root variables. The root variables tell me which root am I in. So in the final solution, Ri will tell me which root I've been assigned to. During execution, Ri's tell me which root am I still feasible to insert into. And usually R0 will stay in that set. That is to say, unassigned will stay in that set until I'm actually assigned a position in a root. So here's an example with root 1 and root 2 as before. So my successor, so 1 has successor 4 and predecessor 2 and is in root 2. I has, visit 2 has successor 1 and predecessor 7. And your start visits have 0 predecessor and our, your start visits have predecessor 6, predecessor, successor 0. Okay, the other variables that we need are accumulation variables. So this is, for each of my visits, I'm going to accumulate various quantities. So the first thing I need to accumulate is the quantity, the load at that point. So Qik is going to tell me the amount, the load of commodity K once I have visited stop I for each of my commodities. And CI is the cost of getting there. So for each visit, I know my objective as I move through the route. If I've got time windows, I need to know the arrival time at my stop and my start time. So if in most problems, I'm allowed to arrive early to a stop and then wait until my time window opens. So I might arrive a little bit early and then start at a different time. So I'm going to have 2 separate variables for those. My departure time is after I've done my service, I depart at a particular time. Now, once again, DI might be considered to be redundant. I can work that out. If I've got a fixed service time, DI is simply TI plus my service time. But by having it as a variable, it opens the possibility of having variable load times. So I might say I've got a load time of 5 unless, so for one vehicle, and a load time of 10 for a different vehicle. So in that case, I would have a constraint that would adjust DI depending on the value of RI. Yeah. And so, as I note there, TI is required, once again, expressivity of constraints. I might want to say something about AI, for instance, penalizing the difference between AI and DI. It's not. It's not. It's the commodity after visit I. So I only need to accumulate, so at visit 1, I need to accumulate however much I've got to for visit 1 for each of my commodities, regardless of which vehicle it's in. Yes, yes. And my objective, and here, so, okay, I've given away another caramello. Can anybody tell me what so I've got, actually, can anybody explain this constraint to me? For a bear? No one wants to try? No, not number of vehicles used. Who was that? Sorry, I couldn't see who was talking. Good-o. You've got a caramello koala waiting for you, Gilles. Yes, so we've got here the cost of travel from every visit to its successor for all of the visits that have a sensible successor, and for those that aren't in the unassigned list. For those that are in the unassigned list, I'm just accumulating the value of that visit. So if I can't visit a customer due to constraints, or maybe I don't want to visit a constraint because the value isn't high enough, then I'll accumulate that penalty in this term, plus the traditional TSP style travel constraints. Okay, so our constraints. I'll talk a bit about this, but we want a path. We want these SI variables to form a path. And basically all that's going to say is that SI, if SI points to, if 1 points to 3 and 3 points to 4, eventually I want to complete a cycle around those SIs will describe a cycle that starts at a start node and ends at an end node. We want an all different except 0 on the predecessors. So yeah, we're allowed to repeat zeros because we've got our start nodes. So on this one, I'm updating my cost variable so getting from me to my successor. So that's pretty easy. Does anybody want to try and explain these ones for a caramello? These 3 here is the ones I'm after. Yeah. So these 2 here just implement. Okay. So this one is the arrival time is the departure plus the travel time, and then I'm making sure that my travel time is my service time is within my time windows, and that I start the service after I arrive. Okay, and I won't bother giving away any caramellos. So the load here accumulates in the obvious way. This is my capacity constraint. I need to make sure that my load always stays above 0, that I start with 0 at my start nodes. So for these start nodes, I'm initializing my capacity and my load and my cost to 0. Here we have some consistency constraints. So the successor of my predecessor is myself. The predecessor of my successor is myself. And the root of my successor is the same as my root. So these are enough to make sure that all of the roots behave sensibly, along with the path constraint to make sure that they stay at the start and end at an end, and no subtours. And then for these 2 here, these are the consistency to make sure that for all of my routes, my start node is attached to the right route, and the end node is attached to the right route. Okay, so given this model, we can, given this CP system, we can model a huge variety of problems. So as well as the VRP and the VRP with time windows, we can do multi-depot, heterogeneous fleets, profitable tour problems. So the existence of that VI term means that we can look at the cost of visiting or not visiting a customer. We can do open VRPs, which is the subject of some interest in the literature. All we need is a special location called anywhere, so that the cost of getting from any location to anywhere is 0. And then we have as the end location of all our routes anywhere, and this turns it into an open VRP. We can do compatibility by simply modifying the domain of either the successor variable or the route variable. And we can do PDPs, pick-up and delivery problems. As I indicated, we can handle variable loading and unloading times. We can handle different dispatch time constraints. For example, for limited docks, we just need a constraint that's going to change that EI, the start value, the start time for my start nodes. We've got depot closing times, and we can even do fleet size and mix, just by throwing in lots of vehicles of different sizes and letting the solver work out which ones to keep. Okay, so if we can't model with what I've just put up, are things like dynamic problems, and that's mostly because of the constrained domain that we've got on our variables. So because I've got this set n and I start off with this domain, I can't actually add in a new visit. So those problems where I want to add in dynamic problems where I'm getting in new orders all of the time, I need to add in indexes to the set, and I can't do that with what I've shown you so far. And we can't decide how many visits to the same customer. So if we've got larger than truckload problems where I've got 100 units at some visit and I've got trucks of size 15, how many visits do I need to make of those trucks to that customer to pick up? I can't model that at the moment either, unless I decide a priori how many visits I want. And this one, because I don't have enough indexes in my cost matrix, I can't do time or vehicle-dependent travel times. And I haven't told you how to do soft constraints, but they can be put in here post hoc. So how do we set this? If we're going to take a pure CP approach, you just want to assign to successor variables. They're your main decision variables, and you'll notice that as soon as if I've already got, well, I'll get to that in a moment. So decision one, just as we were in that animation I showed you of creating a tour, we need to make two decisions. One, which visit to insert and where to insert it. If I choose to insert at one, that is not connected, I can assign, for instance, the successor of 2 to be 1. That's what I call a free chain because it's not attached to a start node. I can do a little bit of deduction on a chain like that, but not as much as if as soon as I attach it to a start node, that's when things really get interesting. Up until then, I can talk about the total load on this chain. I can talk about the amount of time that it requires, but until I connect it, until I route it at a start node, the actual time of delivery and various other things can't be decided. So we've got route chains and route chains that result from these assignments to your successor nodes. You can do subtour elimination as you're assigning to here. So if I'm building on a free chain, all I need to know is the last chain, and all I have to do is remove the start node from the last node on that chain. And that means that I can't wrap around back to that J. This is actually achieved in Comet by the circuit constraint and iLog by the path constraint. The path constraint is actually interesting. It does some extra stuff as well as propagating the subtour elimination stuff. It also propagates cost, and this is a really interesting thing. I won't go into it. You can have a look at this later if you want, but the interesting thing is that why that is that good. It means that you can do some eliminations based on cost, and these are really important in when you're doing repeated solving. So if I've got a standard simulated annealing, what I would do is generate a solution and then work out, once I've got the solution, I'm going to throw my dice and say, okay, the probability of accepting this solution is the change in objective value divided by e to the t, where t is the current temperature. What this lets us do is turn that on its head and work out that I need my objective value to be my current best objective value plus the delta that I have generated a priori. And so now I can stick this constraint of limiting the objective value into my constraint program before I even start. So that now, as I'm regenerating my solution, I can stop nice and if I'm generating a truly horrible solution and I can tell that I will never accept it, I can abort early, which makes it much more efficient. We can propagate capacity constraints for both routed chains and free chains and make use of them, which is nice. So before I assign in a new visit, I can make sure that there's at least one vehicle that can accept this new chain that I've just created. And I can propagate time. So once again, for a rooted chain, I can work out exactly which visits are still possible to introduce into that chain. And for free chains, I can work out the time it takes to travel through that chain, and work out, I get an implied time constraint from that travel, and I can use that to eliminate positions to attach that to the existing free chains. Sorry, to the existing rooted chains. Okay, so some nice things is that the Clark-Wright method that I mentioned before is a construction technique that just assigns to successive variables. And so it's a nice way of using this. And it works really nicely for this type of CP. Okay, but I mentioned before a problem with the representation, and unfortunately what this assigning to SI really limits the type of route that you can construct. And so if I've got this current solution, I can't assign, I can't insert 1 in between 2 and 4, because I've already assigned S2 to 4. CP doesn't like me undoing that decision. So instead, what I can do is create a system that only propagates those decisions that are irreversible. And so instead of assigning S2 to 4, in this situation, all I'm saying is that if I know that I've got this tour in mind, then from 2, I certainly can't get to 2. From 2, I can't get to 9 anymore, because I'm going to go via 4. So I'm going to take 9 out of the tour. Certainly I'm not going to go to 8, because 8 is on a different tour. So 8 is out of the tour as well. 7 and 6 are also silly because they're starts. So I just reduced my domain to 1, 3, 4, 5. So from 2, the only place I can go now is to include 1, 2, or 1, 3, or 5 into this route. And so this is the basic idea. Once I extend it, now 2 can still go to 3 and 5. I might decide to do those next. But now 4 is no longer in 2's domain. And S1 shrinks down to only 3, 4, and 5 as the possible successors. You can also do some propagation based on time windows. So if I know that, assume that all distances are 1 here, and I've got time windows of 1 to 3. For 2, I know I'm going to be at least 1 unit. And because I need to go to 4, and 4 has a time window of 3, I need to leave here at the last possible moment is 2 in order to get to 4 in its time window. So I can do propagations based on that as well. So that's the basic idea of an alternative propagation scheme. In this scheme, I keep an idea of the incumbent solution. Just as I had this idea in my head of what solution I was building up, that is what lives in this box here. And within the CP system, I have propagators and variable value choice heuristics that have an idea of what this incumbent solution is. Now this actually breaks one of the fundamental assumptions of CP. Usually CP variables only communicate via the values in their domains. In this case, we've got this idea of an incumbent solution that's also going to inform these choices. But the result is that you get to do a much richer set of building techniques. And we saw before with that comparison between different choice heuristics on even as simple as which visit you inserted, just how ugly the routes can become, that I argue the benefits of being able to do this richer insert outweigh the ugliness of stepping outside the traditional paradigm. So this allows us to do insertion in the middle, and you're only propagating the non-binding parts of that, the non-binding parts of the decision. So we don't set S1 and S2, but we can, just as we did, I mentioned before, we can remove one from S4 and S6 because they can no longer they're no longer feasible once you've got this idea of an incumbent solution. We can calculate earliest start, latest arrival times, and we can calculate what visits are still feasible and propagate those back into the domains of the appropriate variables. So I'll show you what I mean by that. So here's an example where we've got 5 routes like before, with each of them has a demand of 10 units. Early time is 20 for all of them. We've got one here that's a bit required to be a bit earlier. The others are 150. Have to be back in the depot by 200, and the service time is 10 for all of them. Vehicle 1 and Vehicle 2 have capacity of 30, so at most 3 in a route. And we've also got a request compatibility. R2 and R4 can't be in the same route. So we can pose that, and here is our initial tableau. We've removed, for instance, 1 goes out of the 1 can't be its own successor, 2 can't be its own successor, but apart from that, it's basically our data comes up. And even as soon as we pose this initial 1, we can do some initial propagations. So for instance, the time, leaving each of our start nodes, we can work out what's the earliest time that we can arrive at each of these stops, and that immediately limits our time variable. We can also look at the time windows and say that actually we can't even get to R4 and R5, so these successors can be modified. So what happened there? 0, 3, 0, 1, so 2. Right, if I go straight from our start node to 4, I can't get to 2 in time. So I get to remove 2 from the domains of this successor variable. Similarly for 5, if I go straight to 5 and then to 2, I arrive too late for 2 time windows, so I can take it away. So this is really nice. I never again have to think about going from 4 to 2 or from 5 to 2. So, you know, I've got an efficiency there. My compatibility constraint, certainly I can't go from 2 to 4, and I can't already, 4 to 2 was gone, but I can remove that. So now, even after my initial, with nothing else, no other data available, so sort of a classic routine would have started from that initial data, but already I've been able to make some deductions that it's going to save me time in the future. So now let's say that my variable value choice heuristic chooses to put 5 after 7. I can do my successor implications, so now 8 is no longer a valid successor for 5 because because I'm going to 9 instead. I can do my changes to time and load, so now I know I'm getting back to 9 no earlier than 60, and my load at 5 is no less than 10. I can bind my route variable, because now I'm definitely putting 5 on route 2, and they're complete, and I can go on and do the next one. So with the next one, I'm choosing R2 after R7, so I'm sticking that one in the middle there. I can again propagate my successor implications, update load and time, so now I know the earliest possible times that I can get to these. To R5 is changed, and 9 is changed, and my load. I've got at least 10 when I get to 2, and at least 20 when I get to 5. Depending on, I might insert one before 2 or before 5, so these can still go up. And 9, I've got updated load as well. And I can bind my route variable. As soon as I bind my root variable, my request compatibility constraint kicks in, and I can remove from 4 the value 2 to make sure that I don't put request 4 on 2. Now the nice thing there is that I also get to remove a couple of possible successor and predecessor, or a couple of possible successors for 4 as well, just based on the fact that I can no longer be in root 2. I choose the next one. I update the successors. I update the tone. Now you'll notice that I've updated the load, the latest time here. Why is that? It's because in order to get to R5, I need to leave to start R3, not at the end of R3, but at this time 110. And so I can update these times as well. And bind the root variable, propagate the request incompatibility. So once again, because I've now put 3 into here, 3 goes out of the successor of 4, and I can no longer have 4 or 4 as a successor for 3, because that would put it on the same root. And I now notice that I've got a full root here, and so neither of these can go into root, and so I can propagate those effects as well. I then put 6 after 1 and continue on. I update my latest time constraints based on that diagram, and finally put 1 into the solution. Okay, so now I've got all of my visits in my solution. I can now bind to the lowest value, and I have my complete solution. So I guess what I was trying to demonstrate from that is the fact that by this sequence of successive insertions, I'm getting a lot of information at each step about the decisions that are still possible. I'm propagating a whole bunch of constraints that are saying all of these insertions are no longer feasible. These ones that you might have been thinking about doing are no longer possible. These few visits now have incredibly constrained places where they can go. Maybe you need to think about inserting those soon before they become infeasible. So this is a real strong point of using this method. So it also allows me to do things that affect the solution dynamically. Things like a blood delivery constraint. If I need to go within, need to pick up my blood and then deliver it within 20 minutes of when I pick it up, now I can't fill that with a typical time window constraint, because I can pick it up any time during the day, but as soon as I pick it up, I know exactly when I need to deliver it, or similarly, if I insert the delivery, I know when I need to pick it up. And so I can actually handle that type of constraint dynamically using this mechanism. And drive brakes, I can insert and move around. Okay, that just talks about that. A really nice method for employing this stuff is large neighborhood search. So I mentioned before that LNS destroys and then recreates. So the recreation can leverage this propagation, and it can use the full power of CP. So this is what I talked about before. So I destroy part of the solution, which just means relax some of the variables. And that means move them, basically move the visits onto the unassigned list. And I can destroy things in various ways. I can remove a sequence of visits, so an entire a section of a route, or I can choose the worst arc in the solution and throw that away. And because I don't want to just keep looking at the same worst arc, I can probabilistically look at least worst arcs. And I can choose a couple of routes and say, okay, let's just destroy both of these routes and recreate them in the hope that when I put them back together, they'll go back together in a better way. If they're close, they're more likely to produce a better solution. And I can choose visits that are similar to each other. Choose one and then find another route that's related to it. So a related visit might be one that's close in distance or close in time, close in load. Okay. The usual way of doing this, or my favourite method, is due to Ropke and Pissinger, and what they use is a maximum number to dump. So I might, if I've got a 1,000 node problem, I might say the maximum to dump is 100 nodes, and I'll destroy 100 nodes from my solution and then put them back. Okay, so how do I put them back? Two possibilities, or three possibilities really. One is complete search. And the nice thing about complete search is if I'm using that successor one that I first talked about, I can use just the simple successor. If I'm going to explore the entire space anyway, I use the successor. I don't need to worry about that inserting in the middle trick that I just talked about. So if I've got a very small problem, so if I only destroyed, say, a dozen visits from my solution, I can use complete search to recreate the solution. Or even if I've got a highly constrained problem that's limiting my search space, I can do that. I can use semi-complete search, something like limited discrepancy search is a good choice here. Or depth-bounded, fail-bounded, time-bounded. So I'm doing a structured exploration of a smaller subspace, but not doing the whole thing. Or I can use one of my favorite create methods. So insertion methods is the obvious choice. Because once again, once I've got this partial solution and I'm building it up again, my propagators are going to help me, are going to guide me towards the feasible solutions and the best solutions. So there's a whole bunch, and the nice thing is that you can use a portfolio of insert methods. So a bunch of different insert methods to diversify your search. For instance, I can choose, even if I just limit myself to inserting it in the position that increases the cost by the least, the choice about which visit to insert that we've seen is so important, I've got a number of choices there. Nearest neighbour, I can choose one that's close by, ones that I've already inserted. I can choose a random one, the minimum insert cost that we looked at, and regret. Regret is an interesting one, and it works really well. Regret looks at the difference between the best insertion position and the second best. So for this node here, this is its best position, and its second best is there, which is not that much worse. But for this guy here, the best insertion is there, the second best is bloody horrible. And so what you want is to insert the visit that has the maximum regret. And that way, this guy is going to get its preferred position. And I can extend that beyond 2 regret to 3 regret and 4 regret, which work well. And I can embed local large neighbourhood search within other meta heuristics for deciding what my incumbent should be. I mean, I can just use a classic hill climbing if it's best accepted, or I can use simulated annealing, threshold annealing, and various things. Okay, and one more thing that I wanted to mention is a technique called randomized adaptive decomposition. This is an idea where you, if this is my solution with my roots decided here, I can put in a partition here and then just look at this section of roots. So if these two roots are close together, I can try doing a full LNS just on these ones here. And then having looked at those, I can then transfer my attention and look at just at those and get a better solution. I can then take away that partition and repartition adaptively to examine, which gives you a much better chance of finding a good solution. Okay, so I hope through this that I've convinced you that CP is a natural way of attacking real-world vehicle routing problems. It gives you the power to express the constraints that you're going to see, and a really good tool for finding good solutions. You can introduce new constraints without changing your core solving method. All of that stuff that I was talking about worked regardless of the constraints we're applying. And that once you've decided on CP, that LNS is a really solid way of exploring your search space because it's able to leverage the full power of propagation from the CP engine. And just one more thing, that if you liked what you've heard today about playing with CP and VRP that we've got a position going at NICTA. It's actually doing exactly this kind of stuff, trying to developing CP-based methods for solving logistics, supply chain, and particularly routing problems, working with me and Pascal van Hendenrijk. Lots of CP, working on the next generation Objective CP platform, Canberra-based. If you're interested, look at the NICTA web pages or come and have a chat. Okay, thank you very much. Sorry, as in, I couldn't quite hear the question. Is the question about what happens if a truck breaks down? Yeah. Okay. So the ones I've just been talking about are mostly for pre-planning rather than operational use. So you get the data, you produce a set of routes, they go and drive those routes for the next month or so. Operational things, you need to be able to resolve. And yeah, all of these methods are quite capable of doing that. Basically, you end up starting with the solution that you originally produced. You make the change to your input data that reflects whatever it is that's happened. You take out a vehicle, for instance, that's broken down, and you resolve. It's particularly useful if you've got a vehicle broken down. The value of constraints will help you, the value of customers will help you work out, well, now that I've got one less vehicle, I'm probably going to have to skip some customers. Which customers do I want to skip? It'll be the ones with the least value. So it's just a resolve type thing that we'd be using for that. It really depends. Different contexts have different time limits. So this kind of thing where you're doing a re-optimization once every 6 months with a customer, you can run overnight and it really doesn't matter. We're also using this exact code to do a re-optimization dynamically for a pickup and delivery problem with public transport. In that one, we have to come up with something reasonable in a minute. So yeah, two ends of the spectrum. In the end, all you need is a fourth or a third index on your time thing. That is, it takes me this much time to get from here to here at this time. And actually, a remarkable amount of all of this stuff that I've just talked about all happens automatically. As soon as I introduce a new visit into a route, the time up to that visit doesn't change. But as soon as I update a visit, can I get back to the thing? Okay, so my arrival time equals this plus this. As soon as I change my arrival time by introducing a new successor to I, that's going to update this and I'll trigger a recalculation of all of the SIs following the one that I've just inserted, which will double check all of the time constraints and things like that. The main thing that it lets me do with this system, you can pre-calculate a latest arrival time for any visit. And in order one, work out, is it possible to get to a visit or not? As soon as you get time-dependent travel times, your order one test disappears. And it's actually an order n test to work out, can I get to this one or not?
The performance rate is not too much?
I actually haven't experimented. It's the next thing to do, actually, on my to-do list is time-dependent travel times. Yeah. It certainly will degrade. I don't know how much. because I really want a solution to the problem, I don't care about lower bounds. Lower bounds are unimplementable, and so a lower bound is usually achieved by relaxing some of your constraints. But a problem with where I've relaxed some of the constraints, I can't take that to my customer and say, here's a solution, but you won't be able to implement it. It involves using 3.5 vehicles. I measure my goodness based on what they're currently doing and say, hey, this is a solution that saves you $3 million. That's the thing that's important to them. Academically, I agree, it's very good. And yeah, I guess it gives you a structured way of relaxing constraints, but it's not something that I've looked into very much. I haven't seen a proof of optimality for problems above about 150 customers. And that's kind of particular problems of 150 customers have got a certificate of optimality. But in terms of a general, if I give you one, I wouldn't expect to be able to certify optimality for problems bigger than about 50. Yeah, that's a really useful thing, and something that we're starting to look at now is exactly how, whether you do stuff where you say, here are the possible scenarios that you want to look at, or actually bringing the, for instance, the stochastic demand into a distribution that you then carry through your optimization. They're both things that we're looking at, and that quite naturally feed into this structure. One more, I think. Did you? Yeah. Yes. If you're going to get above, say, 5,000 customers, then pre-processing your customers so that you bundle together customers that are close in time and close in distance makes sense. So that you end up with a little node that has the load is easy, the time is less easy because it depends on which direction you visit them. But usually you can work out an obvious distance direction to visit them, and that gives you a time window that you can give to the blob, and then you end up with half as many blobs to route.
What's the biggest size problem that you have?
Yeah, so. Probably that picture of Sydney was 5,000 customers, but each of those customers was visited on each of 7 days. Although we had this funny constraint that says that the same route, if you get assigned to a vehicle on any one day, you have to be assigned to that same vehicle every day. So that cut down our search space, but that was a 35,000 node problem that we were looking at there. Yeah, so occasionally you do get vehicle routing problems that are, there's the TSP end of the scale, and where you're pretty much free to go wherever you want, and then you sometimes get impacking problems where you've got a total load of 9 and a total capacity of 100, and there you're actually very careful about how to assign the loads. And so sitting a bin packing constraint on top of your system would definitely, those kind of propagations that remove possibilities. So saying, I can't put this visit into this vehicle because that's going to mess up my bin packing abilities later on is definitely going to help. And the nice thing about the CP system is that I can do that without sort of it affecting anything else. Similarly, the scheduling constraints, being able to say if I'm I can make some some deductions based on the time windows, the ordering of time windows and things like that. That lets me eliminate possibilities. That only helps my search.
All right. Let's end it there. Thank you very much.
Cheers.